Okay, let's finish this lesson up. I apologize for that we ran out of time during class. So we were on part B, which is where we said that the sum is of 1 over n cubed is basically the same thing as the partial sum for the first 10 terms, but there's going to be an error, so we're trying to determine in part B what the error in this approximation is going to be. So we've already established that the sum of the first 10 terms is that value right there, 1.1975. The remainder of the first so many terms, n terms, by definition is less than the integral from n to infinity of f of x dx. Okay, and that's why we had to find, up in the top there, that's why we had to find that remainder formula, which we got was 1 over 2n squared. That was the integral from n to infinity. So our remainder has to be less than that. Well, in this case, it's the first 10 terms, so n is 10. So that's going to tell us that our remainder is, less than or equal to 1 over 2 times 10 squared. So 10 squared, of course, is 100, times 2 is 1 over 200. So our remainder is less than or equal to 1 over 200, and as a decimal, 1 over 200 is 0.005. So our value, 1.1975, is accurate to within 0.005. And when you think about what that means, the first two decimal places are not going to change because 0.5 either way is not going to really alter that. I'm sorry, 0.005 is not going to alter the first two. So it's really only accurate to a couple of decimal places. But 0.005 is not bad. And then in part C, it says how many terms are required to ensure that the sum is accurate to within 0.0005. So in part C, we'll do that in red. We want our remainder to be less than or equal to 0.0005, which basically means we want to accurate to 3 decimal places. So our remainder was 1 over 2n squared. We want that less than or equal to 0.0005. So a little bit of algebra here. 0.0005 is going to be the same thing as, let's see, that's 5/10,000ths. So that's going to be 1 over 2,000, I believe. Yeah, that sounds right. So 1 over 2n squared is the same thing as 1 over 2,000, which means that if I take and reciprocate both sides, which I can do, if I reciprocate both sides, that means the inequality sign has to change. So 2n squared is greater than or equal to 2,000, which means that n squared is greater than or equal to 1,000. And 1,000, of course, is not a perfect square. So when you take the square root of this thing, you get that n has to be greater than or equal to, I think it's like 31.62 is what I came up with before. But n, remember, has to count by whole numbers, so it really can't be 31.62. So in order to ensure that this thing is accurate to within 0.0005, I have to kick up n one more digit. So it's got to be n is 32. In other words, 32 terms, or the sum of the first 32 terms, is going to ensure accuracy to 0.0005. That's what that is saying. So the next problem says, can we make this any easier and any better? And the answer to that is yes, we can. But how? All right, so you have to follow me on this one a little bit. recall that the remainder is the same thing as the sum of the whole thing minus the sum of the first n terms. If I wanted to solve that equation right there for s, I would simply add s sub n to both sides. So I would get that s is r sub n plus s sub n. Okay? We're going to go back to the inequality that we started with on the previous page that says I have the integral from n plus 1 to infinity of f of x dx has to be less than or equal to my remainder of the first n terms, which has to be less than or equal to the integral from n to infinity of f of x dx. If I want to replace this right here, if I want to make that s, not s sub n, if I want to make that s from the equation right above it, if I add s sub n to r sub n, I get s. So if I make that middle piece s, that means I had to have added s sub n to r sub n to get s. But if I add s sub n, if I add this to that in the middle, that means I also have to add it to that, and I have to add it to that to keep the balance of the inequality. So my new inequality becomes s sub n plus this integral is less than or equal to the actual sum, and then s sub n plus this integral. So basically what that does is it gives us a way to bound s. We are actually finding a bound for s. We have a lower bound for s, and over here we have an upper bound for s. So we can find those two things. We can bound s and then basically just average the two to get a really good approximation for s. And that should actually take less terms than what we just found up in the previous part where it said we needed 32. So let's go ahead and take a look at this on the next page. We're going to use exactly the same problem that we've been using. According to the formula that we just discovered, though, s is in between the sum of the first 10 terms on both sides, because that's my s sub n. Now, this one is s sub n plus 1. I'm sorry, not s, it's the integral. I know it's going to be difficult because I've got s's and integrals in the same thing here. The integral of n plus 1, well, n is 10, so n plus 1 is 11, to infinity, of our function dx. And this one is the integral, and this is just n to infinity, so it's 10 to infinity of f of x dx. All right, this s sub 10 was 1.197532. 1.197532. Now, to approximate these two integrals right here, using the n to infinity idea, was 1 over 2 times 10 squared. Okay, that was our remainder, basically, using the first 10 terms. And this is right here, this is also the remainder, so both of these are actually just remainders. And this one's going to be 1 over 2 times 11 squared. And again, that's going back to the formula from the previous page. So if you go ahead and work that out, I'm not going to make you guys plug all that stuff in your calculators. What you would get is 1.201 664 is less than or equal to our sum, which is less than or equal to 1.202532. There's not much of a difference between those two things. As a matter of fact, if we average those, then we would get an approximate sum of 1.2021. And if you take 1.2021 and subtract the left side, or you take the right side and subtract the sum, you would actually find out that the error is less than 0.0005. And if you look up here, and this is the part that's interesting, n was 10. We only needed 10 terms using this formula to get to within that accuracy right there. Only needed 10 terms. Whereas on the other page, the one right before this, we needed 32 terms. So this is a slightly more accurate way of doing the estimation if you're looking for the actual sum itself. If you're just looking for the error or how many terms it would take, then you go back to the other page. All right, hopefully that will get you guys through the rest of the homework.